class. So this is the first video for y'all. This is meant as some directions for what to do to continue in the class. So this is kind of like a bit of a lecture, but mostly I'm just going to tell you what to do and what to learn on your own. So first thing I have for y'all to do, at least to start this week off, there's going to be more, is to go and read about applications of Schrodinger's equation, Schrodinger, for a few different cases. So the applications are, so one of the applications, actually we've already talked about this when we were still meeting face to face, before the current stuff going on. It's the one-dimensional infinitely deep well. So one-dimensional infinite well. Of course, it's not infinitely wide, it's infinitely deep, right? Usually the width is given the symbol capital L, or at least in our class it is, in your book. So that's, you might go and review this. Yeah, you'll see boundary conditions, you'll see a differential equation, yeah, arguments about shape, and then you'll get to some answers for the wave function psi, and because this is one dimension, that first dimension is often the x dimension. And then you could, yeah, so psi of x, and yeah. Okay, so after that, this is not necessarily the order presented in your book, but go and check out the two-dimensional version of the very same thing, the two-dimensional infinitely deep well. And in this case, you're going to end up writing down a wave function that's actually a function of two different variables. Yeah, so check that out. It's pretty cool. It runs basically the same way, except for there's something really new, or at least it's a new technique so far in this book, although you've probably learned about it in your differential equations class or other classes, even in engineering. It's called the separation of variables technique. This is a big deal. And something else that's new that shows up is called degeneracy. And in particular, it's the degeneracy of the energy value, or the allowed, or the energy level values. Yeah, so two-dimensional infinitely deep well. Also, go and check out, it's the very same section in your book, the simple harmonic oscillator. So and of course this is the quantum version because you're going to use Schrodinger's equation. You're going to, yeah, so simple harmonic oscillator. Sometimes this is abbreviated SHO, and I'll probably sometimes do that absent-mindedly. So, and in particular, you're doing this in 1D, but you might imagine, could you also do the separation of variables if you had a two-dimensional or even three-dimensional simple harmonic oscillator? And then the last thing you're reading about is the finitely deep. Confining well in one dimension. And interestingly, for some energies, you will have confinement, that is, the probability, you might say the probability of discovering the particle far away from the center of the well goes to 0 as you go further and further out from the center of the well. But there's also free versions as well, where a particle does have enough energy to get out and stay out of the well. So this has both types of solutions. It's a pretty neat situation. And in this case, your book will bring up the fact that there are non-analytic issues while you're trying to do the math of this problem. For example, when you're trying to normalize the wave functions that this thing gives rise to. So that's what you're doing. The homework that's appropriate for this stuff is in the same chapter. It's chapter 5 in your book. It's problems 15, 17, 19, 21, and 25. And what I thought I'd do is actually real quick talk about each one of these problems. And so when you do go and you go read through this list of topics, your mind will be sparked for the individual issues in these problems. So let me do that real quick. Oops, let me actually, I forgot. Let's add one problem at the beginning. It's a simple problem, number 13. So number 13 is normalization. And you might, this is a normalization problem, and you might try to remember, why is this important? What's so important about normalization? Right? Because it's some basic physics reason or basic interpretation reason why normalization is important. Number 15 is a problem. When you go and read it, it's trying to get you to model, oops, not two L's, model a real problem, but real in quotes. So there is some data. It wants you to consider a confined particle, and so what you're supposed to assume is that the particle is confined inside of an infinitely deep potential well. That's the only way you're guaranteed this perfect confinement. Otherwise, with finite wells, there's always leakage out the boundaries. Another interesting comment to make for number 15 is that it gets you to, it's really just some like words essentially. So second excited state is n equals to 3. So this 3 and that 2 don't match, but if you think about it, the first excited state is an excited state up above the lowest state. So the lowest state is called the ground. The first excited state, that's n equals to 2, is, the first energy above the lowest, and then n equals to 3 is the second energy above the lowest. So that's n equals to 3 is the second excited state. Number 17, I'd like to point out to you, when you go read this problem, it's pretty cool. It's a infinite well problem, though in 2 dimensions, and it says that the energy is proportional to the sum of an integer squared plus another integer squared divided by 4. And I wonder if you can go pick out the reason for the 4. It's pretty simple when you go and you inspect it. But yeah, it's a consequence of the separation of variables and yada yada. But go check it out. See if you can follow that number 4. Number 19 is a problem of enumerating states, quantum states. That is just listing them all out and keeping track of this new concept you're learning about called degeneracy. So enumeration of states is just list all the possible states out, all the different states. That just means they have different quantum numbers. Number 21 is about the simple harmonic oscillator and classical turning points. So these classical turning points it's about the classical problem So if you have a harmonic oscillator, a classical one, that's just a mass on the end of a spring. And this little mass, when you put energy on this oscillator, this little mass just goes back and forth like this. And it has these turning points at which the oscillator doesn't have energy to be able to go beyond. So these are called the classical turning points. So it just oscillates between the 2 points. You'd say that if you were to write down an equation of motion of this, this would be the amplitude. You know, x naught times sine omega t would be the answer to the motion of this thing, classically. And number 25 is again about simple harmonic oscillator turning points. All right. Thanks for listening to me.